Hi, today we gotta go over what polar molecules actually look like and what they need. So, first, to be a polar molecule, I need to know if I have polar bonds. If there are no polar bonds, it is impossible to have a polar molecule. Polar molecule needs polar bonds. The second thing I need is a partially positive end and a partially negative end. It doesn't matter if the partially positive end is on the top, partially negative is on the bottom, but as long as I can touch both the positive part and the negative part, I will have a polar molecule. So let's check out a couple examples. All right, let's look at carbon tetrafluoride to see how it is. So first I look at their electronegativities. I see that carbon is 2.5 and fluorine is 4.0. So I know that the difference is 1.5. Remember, I always take the bigger number minus the smaller number. It doesn't matter which order I write them in. Because the electronegativity difference is 1.5, that tells me I have polar bonds. So I have that unequal sharing. So I still have to do my structure the same way I've done the structures before. I know that carbon has 4 valence electrons, and I know that fluorine, there are 4 of them, and each of them have 7 valence electrons. So that's going to give me a total of 32 electrons. Now, remember, I don't really care about electrons as much as I care about their pairs. So I'm going to divide that by 2, and I'm going to get 16 pairs. So I start by drawing carbon in the middle. I have a fluorine coming off each direction. And I connect each of those with a bond. So instead of I've used 4 out of my 16 pairs, so I've got 12 pairs left. Now I'm going to place those lone electron pairs. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's see. Yep, and 12. I just can't count. So I placed all 12. I've got none left. So when I check everything, carbon has its 4 bonds around it, so that's its 8 electrons. The fluorine on the left has all 8. The fluorine on the top has all 8. The fluorine on the left has, on the right has all 8, and the fluorine on the bottom has all 8. So now I've got to remember those bonds are polar bonds. So I need to draw my dipole. Remember, my dipole always points to the more electronegative. So I know fluorine is more electronegative than carbon. So I'm going to draw my dipoles for each bond facing out. Carbon is the partially positive, while fluorine is that partially negative. Yep, as I write a fluorine. So I can see that all of my bonds are going to be pulling in a tug-of-war kind of situation where everybody's pulling on that poor carbon, and they're all pulling equally in opposite directions. So just like a solid tug-of-war match, they're going to cancel each other out. So while this has polar bonds, that's the first step, it is a non-polar molecule because all of the polar bonds cancel each other out. They're all pulling in opposite directions, so there is no partially positive side of my molecule, there is no partially negative side. So look at the next example. I've got sulfur dioxide. So I know the electronegativities of sulfur is 2.5, oxygen is 3.0, so I know that is a 0.5 difference. Once again telling me that I am a polar bond because 0.5 to 1.7 are what we're using for that cutoff. Remember, we're going to use a black and white world. So I know I've got polar bonds. So I'm going to make my molecule just like I did before, where I show the sharing of the electrons. So sulfur has 6 electrons, and oxygen has 6 electrons, and there are 2 of them. So 12 plus 6 is 18 electrons. Remember, I don't just want electrons, I want pairs, so I divide by that I divide 18 by 2, and I get 9 pairs. So I'm going to draw my sulfur, and I'm going to draw my oxygen, and I'm going to draw my oxygen. So that takes me to 7 pairs. From here, I'm going to put my lone pairs. So I'm going to start with my central atom, and there are my electrons for that central atom. So instead of 7, I'm down to 5. So then I'm going to put 1, 2, 3, 4, 5. So I'm out of electrons. When I check my bonds, I look and see that sulfur is good, one of the oxygens is good, the other one is not. So I'm going to need to take a lone pair and pull it in to make a double bond. And that gives me my sulfur dioxide. From here, I need to figure out if my molecule itself is polar. Well, this one's a little bit harder to see because that lone pair actually pushes those oxygens down a little bit. So I will always show you that structure so that you can physically see that, but we have to sort of imagine that those oxygens are down that little bit because those electrons like to hog more places. So I know that my oxygen is a 3, my sulfur is a 2.5. So when I draw my dipoles, I'm going to draw my dipoles. Let's try again. I'm going to draw my dipoles pointing towards my more electronegative, which would be my oxygen molecule. So my dipoles are going to be going out. Now remember, this molecule, I'm going to draw it on the next page just so you can see what it looks like. When I draw this with the electrons up there, it looks much more bent. Those electrons are going to push the oxygens down. So when I draw my dipoles, remember they're coming towards the oxygen. To figure out if I have a polar molecule, first I look if I have polar bonds. Indeed I do. Second, I look if there's a partially positive side and a partially negative side. Well, I can see that this sulfur up here is partially positive because all the electrons are being pulled down here towards the oxygens, just like the penguins and the polar bears, where the oxygens are your polar bears and the sulfur is your penguin, and the polar bears are able to steal that ice cream cone a little bit more. Down here, my oxygens are partially negative. So the overall polarity of my molecule is simply drawn one of two ways. I can either use those funny sort of looking 8 symbols, or I can just draw the dipole arrow to show the overall polarity of the molecule.